I'm sure most of you here are cybersecurity experts, aren't you? Huh? So I'm not that special. So I'm gonna start with a little background as how I got to this idea. It's been brewing with me for some time, actually. So it was 2010. I was studying in Sweden, and I had a great idea for my master's thesis. I was gonna try and understand Skype. Some of you may not remember anymore, Skype was that cool technology where you could chat and send pictures and videos and everything, right? No one uses that anymore, but 6 years ago it was their thing. It worked everywhere, so there were many questions about how it works. Is it secure? Is it backdoored? Is it really peer-to-peer? Are someone listening in on our conversations? So I selected that as my preliminary master's thesis. Some of you may know I did not actually finish my thesis using that topic because Skype lawyered up. So I was living in Sweden at the time, and I heard a doorbell one day. There was a gorgeous blonde woman standing at the door, but unfortunately she didn't want any fun. She just wanted me to sign some papers, so signed receipt of some super important, super secret document. I've actually given a short presentation on the legal side of all this story at 27C3 a couple years ago, so you can look that up. But basically Skype said, well, you got to stop what you're doing, delete everything, and never use our product again, which I happily obliged, the last one I mean. So I was, how it happened, I did not have proper anonymity, so they found me. In the end I didn't have to pay anything, but they went after me for a year and a half, even after I changed the country. They found me, again, a letter in the mail. So it happened probably because I was dumb. I used my real name, real country, Sweden, in my Skype profile. They were smart. They had access to some databases, access to lawyers. So I learned that having real name and telephone number is a luxury you don't usually need to take to use services. That's why I don't use WhatsApp, for example. Well, there's a better reason now, 2 weeks already. But also I became interested in the technical part of anonymity, and that is what this lecture is about. So a little bit about me. I myself come from Latvia, not Sweden, where I was studying. This is my first time at Balkan. And like many of you, I started programming when I was 7 years old. But I started doing that on a home-brewed computer. Now, don't get me wrong, I didn't solder it. I didn't know anything about electronics at that point. But some of my relatives made it, and they moved to a better occupation, so they gave it away. And 7 years old, I started mashing the buttons and drawing circles and learning about sinuses and cosinuses and stuff like that. So that's probably a story for at least some, I think many of you here in this audience today. What was different at that point is that, not like most of you probably, I did not have access to the internet for the first 8 years of my working with computers. So it was a fun time. It was a different time. You had to actually keep a lot of information in your head. No online lookups of function parameters you forgot. So PHP could not have lived back then, right? With all the random sequences of function parameters there. So yeah, I started programming, and then I gradually moved to administration. That happened through hacking. So I was in the 7th grade. That's approximately 7 years later, you know, pupils often get fed up with their teachers. So I got fed up with one teacher. I don't remember the subject, and I decided I should spoof an email. I should use her source email address to write a terrible email to one of the admins in the school I was studying. So choosing the destination address as one of the admins was probably not a smart idea. I did write it. It was an ugly email, and to my surprise, a week later they found me. Even though I took the precaution of going all the way to a different apartment in my building, to my friend's apartment, they actually managed, of course, to look at the header, find the IP address, find the real home address, and look the pupil's database where, you know, my address was only different by the apartment number, so they got me that way. Also, during that period, I tried to mix my programming skills with this new administration thing that was going on. Some of you may remember a program called Windows 95. There was an exploit for it called WinNuke. Who knows WinNuke? Okay, couple old people here that do. Okay, I'm old too. My doctor said that I'm finally old. I went to him 1 month ago. Said, sorry, you're old. Nothing we can do about that. If only I knew. So anyway, WinNuke is a fun story. So remember, I didn't have internet at home. So I looked up at the spec of the exploit online on scripty level right at school. I went back home when I had more time. I opened I think it was either Visual Basic or Delphi. So I opened that. I wrote in my payload everything. I tested it on my computer. So I had one computer at home, right? I tested it. Bam, got the blue screen of death on my computer. Perfect. So no other computers to test on. So went to school, tested, wrote an IP address of a neighboring computer. Perfect. Blue screen of death there. So it worked by using NetBIOS, TCP 139. You set an urgent flag on. Well, that's beyond the point of the presentation. Anyway, so I thought, okay, but you know, people use these cool things called DNS names to refer to computers, and I could just type. And at that point at my school, all the computers had local domain names, 4-letter names, really easy to type. So I thought, well, I want that additional functionality in my cool exploit here. So again, I looked up the manual. There was a function called get host by name. So I added that inside. I tested it at home. Again, my only computer, no internet, it worked. Blue screen of death. So I went back to school. Again, I sit at the computer, look at the host name on the computer on my left, type it in, press the button. Suddenly my computer gets blue screen of death. I thought, shit, well, okay, gotta fix that. I look left, that also worked. Great. I look right, that also worked. I turn around the classroom, all the computers got blue screen of death. Apparently also computers not in the classroom. The whole school was a single subnet, so everybody got blue screen of death. I quickly shut the thing down and went away. So I don't know if they know that it was me, but so apparently function get host by name returned -1 in case of an error. So I didn't configure DNS servers or something in the code, so I got -1. And then we have this signed, unsigned integer thing, right? And -1 is also FF, which in decimal is 255 4 times, which is broadcast on a network. So a small bug there. Anyway, so here today I'm going back to my roots. I'm still an inventor at heart. Even though I work mostly with security now, I moved on to that, of course, and recently also cybersecurity policy paperwork. No real damage there. But I wanna talk to you about something I hope I invented. I mean, I did a Google search. I didn't find anything like that, but I didn't do proper academic lookup. Maybe someone already described this like 10 years ago. That would be a bummer. Well, okay. So what is this talk about here? I want to introduce SIPSA to the world, and I want to have a discussion with you guys and gals here on real-life applications of the technology, and I also would like to hear your critique and comments on my proposal. Of course, code edits are very welcome too. So I think it's really important for everyone to be able to follow what I'm about to tell here. So I'd like you to be able to do that regardless of your background. So those of you how many of you have a networking background in your professional or hacking careers? Oh, a bit less than half. Okay, so I want everyone else also to understand what I'm talking about. So we're gonna go through some basics. We're gonna cover ISO OC model with all the layers. We're gonna look at TCP and UDP. And again, I want to emphasize, I think understanding the basics is really important. I remember myself in lectures at the university, sometimes, you know, you're a bit bored, then you suddenly miss a topic, and then the rest of the course is unintelligible to you. You're just basically useless. So I don't want that to happen. Okay, so we're gonna spend some time here on this chart. This is of course known as the ISO OC model. It's one of the ways how to look at data that's traveling a network, that's traversing a network. There's also the TCP/IP model, which is simpler. It basically groups layer 1 and 2 together, then we have 3, 4, and groups 5, 6, 7 together. But this allows for more precision. I somehow, you know, the academic in me wants to use this, which has more detail in it. So let's talk in detail about what it is. Out of the picture here is the media, the wire, or whatever the media is. It's on the bottom there. So your wire is there, and on the top, let's call it layer 8, is the user. It's you sitting at your application, at your computer. So when you type something in the application, it goes through all the layers to reach the media. And when information comes to you, when you receive an email, for example, it comes from layer 0 all through these layers to reach you on top of layer 7. So let's take a look at physical layer here. So in physical layer, the one piece of information we have, it's called a bit. All of you have heard of it, I'm sure. 0 or 1, right? And physical layer includes some method of representing bit, Manchester encoding for legacy Ethernet, the slow one. And it also deals with the physical representation, of course, of your bits. So, for example, on the wire, you might have voltage levels, actual voltage levels, like real world. That's where we have the real world on layer 1. We might have optic fiber with different patterns of lasers going in. We might have a radio if we're using Wi-Fi or some other obscure protocol. We might use pigeons. There's actually, I think, an RFC on using pigeons for transmitting. You can actually do Twitter over pigeon, I mean, if you have the physical layer set up. So the goal of physical layer is to transmit and receive raw streams over the physical medium. There's nothing much a theoretical scientist can do there. So let's look at layer 2, the data link layer. It's a layer that contains the MAC address, and this is where non-network people should really listen in. So MAC address is supposedly a unique address assigned only to your network card in your device. It consists of 6 bytes. It's usually represented via hex, like starting 00 up to FF and delimited with colons. We're gonna have a demo in the end, so you should understand that. So we have frames on data link layer. It's just how it's called. Data link layer is only relevant on the same physical network. So its goal is to allow for reliable transmission of frames between nodes that reside on the same physical network. So unless there is some physical medium connecting to two nodes, data link layer alone is not enough. We will need to go up to network layer. Layer 3, the network layer, it contains the packets. Oh, right. For data link layer, an example, Ethernet. Right. So network layer. it contains the packets. And here we know, of course, everybody knows IPv6. Then there's also a more obscure protocol called IPv4 that's also sometimes used. And ICMP is another example I would give. Network layer deals with routing, traffic control, and internet addressing. In the original idea of how the TCP/IP model was created and how the founding fathers wanted it to work, apparently you should be able to select a source IP address and destination IP address, and it would not change for the lifespan of the packet. It would actually reach the destination computer that has that IP address. IP address is, of course, a part of the network layer packet. At layer 4, the transport layer, we add a thing called ports. So for each IP address, let's call it computer, for each computer you can have a specific port starting from 0 to 65,535. Port 0 isn't really used, but you can actually use it, but it's a different hack. Not going to talk about that either. So examples here, TCP and UDP. Segment is the name for data on layer 4 if you're using TCP, so that's segment, and the datagram is for UDP. So we're going to have separate slides on TCP and UDP. Now, we're not going to go into details on the upper layers, in part because they always confuse me. I mean, the division between layer 5 and layer 6 is really blurry for me, I think for most of you, right? But data is called data on layer 5, 6, and 7. It's basically your application, whatever you have, like Apache, with or without TLS. Your application on top of Apache, that's all in there. And then we have a user on top. So final thing I want to say for this slide here is there is a process called encapsulation and a process called decapsulation. Encapsulation simply means going from the user down through the through what we have here on the screen and encapsulating the user data, adding different headers and footers to it. So if, say, you want to send an email that says that teacher is a skank, then you would have that on what we call layer 8, and layer 7, 6, and 5 would encapsulate it, maybe change something, right? If you have some special characters in there, they would be changed on these layers. Transport layer would add a port in 25. Network layer, through some quite complicated process, we would have found out the IP address. It would have the IP address of the mail server where the mail is about to be delivered, and of course the source IP address of my neighbor. Data link layer would contain local MAC addresses on that network segment, so those would change when the frame is destroyed and created as it goes through the internet. And physical layer, of course, depends on the medium. Right, and decapsulation is the same. So for every network device, it goes down to the physical layer and then back up. Okay, so let's take a look at TCP versus UDP. Let's compare these two popular layer 4 protocols. So features of TCP. TCP is a stateful connection-oriented protocol. It means it remembers the state it's in. It doesn't have to send all the previous data relating to your session with every packet. With every segment. It actually has enough information so that computers and other network devices have to remember what's happening there with TCP. And it allows for creation of connections. We're going to take a look at that right in half a minute here. It provides what's called reliable transport, meaning that it really tries hard to deliver the message. Hey, the two of you should come back like in 10 minutes when we're talking about the real stuff. I know network guys, sorry, it's a bit boring, right? Okay, so it's kind of reliable. I mean, it really tries to make sure the message is delivered, and if it isn't, it tries again. So it has some notable features. For example, the three-way handshake. So one more thing TCP has are flags for the TCP segments. There are numerous flags, like around 10. Three-way handshake is a process that tells two parties, two IP addresses, client and server, that the connection has been established between them. So a packet with SYN flag set is sent, server replies with a packet that has ACK acknowledgement and SYN flags both set, and then the client finally replies with a packet that has acknowledgement flag set. And that creates a connection between them. Now, each of them, including all the devices in the middle, remember that a connection is open. Of course, the connection can also be turned down when it's ended. The party that would like to close the connection sends a packet with FIN flag set. We get an acknowledgement and FIN back, and then we send an acknowledgement. So the only thing changes is SYN changes to FIN. It's quite an easy protocol, actually. So it also has error detection like checksumming and confirmations, the acknowledgement flag we talked about. It allows for ordered transfers. So all the segments have sequence numbers, and as packets and segments within those packets would sometimes take different paths on the internet, they might come to the recipient in different order. TCP allows for that to happen, and it's fine. It actually reorders them in the correct order at the destination. And flow control. Since hosts have different network quality and network speeds and latency, it is important. TCP has also something called window that allows you to control the speed of flow. But let's look at UDP. It's more useful to us here for this talk. It is stateless and transaction-oriented, so hosts are not required to remember anything about UDP session. Let's call it session because it's not a connection. This is, but intermediary devices like firewalls or routers still try to infer when a UDP connection is happening just from the metadata. Some Encapsulation actually has a nice hack that uses this feature of UDP that allows to connect two hosts behind the NAT without a middleman. You should look that up if you haven't heard about that. So it is a best effort transport. It just sends a packet and that's it. I mean, if it's delivered, that's fine. If it's not, no one cares. So some notable features include it's simple. It has no control mechanisms and it doesn't transmit the data again. So this is the UDP datagram. It has just the source port, destination port, length, checksum, and the data. So it's really simple, even like 10 times more simple than TCP. We had guys saying that 75% of statistics are made up. I just made up that number 10 times, but well, it's simple. Okay, so UDP is perfect for what we're trying to do here. Let's look at anonymity on the internet. Here's a comic for you. So you have seen that, right? On the internet, nobody knows you're a dog. So anonymity on the internet kind of exists, right? But I found one more comic here. So here's a host saying that our next guest has chosen to remain anonymous, so he will remain behind the screen during the interview. Please welcome Mr. Isaac Phillips, age 26, from Amarillo, Texas. So is anonymity on the internet real? My Skype story tells no. The fact that we have Tor also tells us something. But is Tor effective against state attackers? The current research, which Tor community eagerly tries to ignore, says no, it's not really effective, and I joined the research in that opinion. So one final thing on the network. Here's the random network diagram I pulled from the internet. So let's talk about how routing works on layer 3. Earlier in this room there was a talk by Ganimo, and it was titled, "Why Can't We Have Nice Things?" Well, this slide should explain why can't we have anonymity in the network. So we have 3 networks here indicated by those blobs of different color. We have 2 routers. So how routing works is that when, for example, this PC1 on the bottom in the yellow blob tries to connect to PC3, it has to set the IP address somewhere, well, it usually sets the IP address to the IP address of PC3, so 30.0.0.3. Otherwise, the routers in between, indicated by the router symbol, and having text router below those, would not know which interface to forward it through. So say PC1 would like to send data to PC3, but would like to anonymize the destination address. Say, send it to 10.0.0.2. Router 1 would actually send information to the blue blob instead of the green one, and PC3 would never get the data. So changing IPs or hiding IPs in layer 3s leads to a fail. So we have a problem. IP alteration fails. IPs on layer 3 are needed for routing. That's why we can't simply remove them from there. We cannot encrypt them. Of course, we have IPsec, but it's a different story. It doesn't really work. So yes, we have a problem here. So I propose a solution. Use more bandwidth. So the hack cons that I frequent often have this sign up. First years at the hack cons, I was wondering why. Why do they have this sign up? I really couldn't understand that. But well, as years went by, I think I figured it out. So the bandwidth has been paid for, so why not use it, right? This is a real statistic. It's not invented. So more speed everywhere is what we're getting. In my hotel here in Serbia, my peak speeds for the Wi-Fi in my hotel reach 4 megabytes per second. I'm lucky, right? Not everybody has that kind of hotel, but I mean that's something. In Latvia, where I come from, a normal home internet connection is usually between 100 megabits per second up to half a gigabit per second. We are, I think, the fourth country in the world ranked by internet access speeds. So Japan has it better. So let's fill the bandwidth then. We need more datagrams. It is a statistical solution that I will provide to you. It statistically makes it less likely for an adversary to determine your IP address. So all the network gurus should now pay attention again. So we finished with the network intro. Okay, so I present to you SIPSA, Source IP Spoofing for Anonymization over UDP. Let's look at a small overview of how this technology works. SIPSA protocol goes on top of layer 4, but below layer 3. So here's a cool diagram. So you could consider it a tunneling protocol this way, because it allows layer 3, where the real IP addresses are, to be incorporated on top of it again. But it's actually, if we look at the network stack on the wire, it looks as layer 5 protocol from that perspective, and we will see that in Wireshark, of course. If someone wants to write a patch for Wireshark to interpret this, they're more than welcome. So the idea is sending multiple UDP datagrams for each single datagram that should be normally sent. Idea is easy enough. In those multiple datagrams on layer 3, the IP addresses are replaced. The source and destination IPs are randomized. So, for example, we would get one real packet with a real source and IP and 63 fake packets with all the possible combinations of fake source IP addresses generated and fake destination addresses generated. Also, the current version uses the IP generation in pairs. Why is it important to use them, to generate them in pairs? There's something called BCP38, which we'll have a slide on much later today, in this presentation though. BCP38 might block stuff going from different subnet. So just to make sure, we also create one IP address that is in the same subnet, well, in the same class C. But if we had just that, then it would be easy for the adversary to find the real subnet. So we do that for all the subnets, including the fake ones. Protocol, of course, allows for expansion and version support. That's possible. Current version, version 4, chooses IPs within Class C network, so we don't bother with finding the actual subnets. It's irrelevant for an attacker outside your network. So, and metadata currently includes the real IP addresses and the list of the fake IP addresses used in an encrypted form. Payload is not encrypted because we have TLS for that if someone wants to do that, or any other type of encryption, IPsec, whatever. So a single TCP packet is being sent here. I have a question to the audience. Which IP addresses is communicating with which? Any guesses? You can refer to the right answer by the line number. I can see. Okay, so one more thing SIPSA does is it always selects the same list of fake source and destination IPs for specific network parameters. So, and those parameters include real source and destination IPs. So that's thought about. Anyway, the right answer is line 25, but as you can see, it's not really possible to do that, to figure it out from this screen. So it should work, I think. But right now it's a nice addition with a lot of asterisks. And we'll of course discuss possible problems with that. So this is my proposed format as implemented in version 0.4 of the protocol. I hope everyone can read the fonts there. So we have a header that just ASCII says SIPSA in ASCII, 5 bytes. We have a reserved byte that's always 0. At first I had a version number there because the first iteration of the protocol, the version number was also ASCII, which was a waste of time. I decided to make it binary. So now we have reserved byte there, which is cool. We can use it. We can set it to 1 when the protocol is actually used in production. Okay, so version byte says has version 0.4 in this example, in this version of the product. Then we have length of the metadata. It's divided by 16 bytes because we encrypt the metadata and we can save space that way. So there's also a limitation here. You cannot have an infinite number of source and IP addresses in this example because it has to fit in 16 by 256 bytes, multiplied by 256 bytes. We have the initialization vector, 16 bytes. It's random for every original datagram and the same for every duplicated fake datagram. And then we have a block that's encrypted with AES 256, CBC mode, 16-byte block. Total size of that can be found by the formula metalan -1 times 16 bytes. Now I should stress, and I can't stress this enough, that even though I've taken some crypto intro in university many years ago, I'm not really a crypto expert, so probably that crypto is insecure. Don't use that in production. But it's well, I couldn't break it, but you can never break your own stuff, right? So and then you have the payload. So here's an example of the datagram. It's nicely colored, so we have. Oh, you can't see the blue one, but it doesn't matter. It just says layer 3, so that's the underlying information, whatever that is. Layer 3 is where the fake IP addresses are. The blue one you can see. And then we begin with SIPSA in dark blue, and then we have all the information there. The larger portion in brownish is the encrypted part, and then payload is in plain text, as you can see. It starts with E45, so it starts with layer 3 IP packet header. Okay, now let's take a look at BCP38 real briefly. It's a best current practice. So this slide talks about why things aren't as good as they could be. It's 16 years old, so it should be implemented everywhere, right? Well, it's not really implemented everywhere. It talks about network ingress filtering, which means that your provider should check the source IP address of your computer to make sure that it's within the range. Fake packets are not forwarded. This is supposed to solve denial of service attacks. It does not really solve them. I mean, it worked well for some time for the networks where it was implemented, but it's not widely adopted, and new denial of service techniques have emerged. For example, botnets, and these techniques don't rely on source IP spoofing necessarily. So let's take a look at SIPSA results, the good, the bad, and the demo. So BCP 38 has been sparsely implemented, which allows us for greater success rates. SIPSA may provide an additional layer of anonymity. It needs to be combined with other techniques, though. It also provides deniability. UDP doesn't do acknowledgements. If you configure your box correctly, UDP also does not send ICMP unreachable packets. So if you make sure to do that, it really allows for some nice legal magic to happen. I'm not a lawyer. So it also uses fixed symmetric port numbering, which should confuse the attacker about the direction of the connection and if a new connection is initiated or not. So the deniability goes like this. Imagine an investigation happens for some reason, and so SIPSA gives you a possibility to answer to the judge, "No, Your Honor, my devices neither requested nor acknowledged receipt of the communication in question." And you can get your torrents, not acknowledge any packets, and say that some bad guy just sent it to your IP address. Or do something, you know, torrents of Ubuntu, ISOs. Okay, so the bad things here. I think BCP 38 is not going away. It's being slowly deployed on additional networks. SIPSA gives only statistical improvement, not 100% vulnerability, not 100% anonymity. So statistical attacks are likely possible. In addition, of course, the statistical attacks that I found possible against my crypto here in this version 4. Success largely depends on internet service providers that you use. It increases the network load, but hey, we have bandwidth that we paid for, right? So these are the tests I did for a large datagram of 60 kilobytes. For smaller data, you will see a more significant increase in the network load. So if we configure SIPSA to use 3 source addresses and 3 destination addresses, including the real one, it would result in 8 times more network traffic being transmitted. 2 by 5 source and IP addresses, it's 9 times increase. 6 by 6, it's 35 times increase. Starting with 8 by 8, we can actually use a formula to determine the increase. It just count of source IP addresses by the count of destination IP addresses multiplied. So 8 by 8 gives 64 time increase and so on. 100 by 100 gives 10,000 times increase in network loads. So, okay, I think it's finally time for the demo. Can we get that going? Okay. So I should have opted for the longer cable, but okay, it's gonna have to do. Okay, so for those of you with laptops and nothing better to do, I want you to follow this as a hands-on. If you have 2 machines available with real IPs, so somewhere on the internet. So my GitHub is github.com/0ki, 3 characters, 0ki. So I found out yesterday that there are no real IPs here on this network, which is unfortunate. So I scrambled to create a virtual network this morning on my laptop here, but it actually works over internet. I tried it. So okay, let's. I'm going to show you the network setup I have. Okay, so I have 3 virtual routers, 1 to 3, and my laptop is going to act as sender in one of the networks there and receiver in another network there. You can see the schematic here. Since I only have 1 laptop, I needed to make a small hack in red on router 3 in order for Linux kernel to play ball on the sender and receiver machine. So sorry for that. I will actually be sending a packet to 10.57.571, and router 3 will do a destination NAT to the real IP address of the receiver. So don't kill me for that. But everything else is as it should be. So let's start up the network. So who of you here have heard of MikroTik? Oh wow, okay, it's a great Latvian company. Makes great network products. By the way, can you hear me okay, and on the recording if I speak like that? Yeah? The microphone works like that. Okay. Let's assume it does. Okay, so let's start my 3 routers here. And I will also set up routing on my machine here. Sorry for using route instead of IP route, I still can't get a hang of it. Okay, I will add, so remember the schematic here. I will add the default route from this machine. We're going to be sending from 192.168.562 to the router 2 here with this IP address. Okay. So, oh, we have that, right. Good. Now let's take a look at the product. Okay. This is from my GitHub. Now, if I launch the client, you will need the root, of course. That's one thing. For the server, you do not need root. So I'm going to launch the server. But even so, if you have root, I have a check built in for fake. Oh, sorry. For private IP address space. So we're gonna do a little bit of editing and also take the opportunity to take a look at the source code. Let's get colors. Oh. Okay, no colors. Well, never mind. So what we want to do here is we would like to remove this warning here, as suggested by the warning itself. We will change the destination from this example address to the one on our network diagram. So 10.57.57.1, and we need to create a secure key. Right here. So I have this cool badge here. Let's give a round of applause for creator. It's really good stuff. So okay. I'm gonna take the password mode, and I'm going to hope that I have a password here in this socket. Okay, right. Here it is. We also going to need that in the server. Right, permissions. I'm going to copy this to the server so it can understand the packets. And finally, in the server, it usually listens on all the interfaces, but it wouldn't be fair. So we want to listen only on the interface of the second simulated laptop. So that is 10.57.1.1. Okay, let's try it out. So we can run the server, the receiver part as normal user. And let's run the client as root, because it crafts packets on low level. Oh, right. So it's a kernel screwing with us again. So we need to specify a source address too. So since we have multiple IP addresses on this machine, we're just gonna add a small hack here. Instead of finding it dynamically, let's specify it manually. And let's run it again. Now, it worked. If you guys do applause here when demo works, you can do that now. So the server actually received 5 different packets of the ones being sent. It decrypted and found the IP match and printed the data inside the payload of SIPSA here, starting with E, which indicates IP packet. Let's take a look at Wireshark. So we're now looking at the network of the sender. We can see all the addresses in there. And as you can see, beyond layer 3, it's identical. You can see that on the right. And you can also see, of course, that data, the payload, is unencrypted there. If we look at this, we will be able to count 5 times 3, I think 15 packets. Right, 15, yeah. And now let's take a look at the receiver network. So the receiver network clearly receives, stop hacking this. Clearly receives only the 5 packets that where the destination address matches. So we got a statistical probability of 20% of guessing the real source IP address there. Okay, can we move on back to the slides, please? That's not my slides. Let's have my slides. Okay, so I hope the slide is coming up. So what I would like to finish with is the future testing and research of SIPSA. And I would like to talk about possible improvements to anonymity, general security, and of course some other features. So it doesn't mean I will do all of that myself, so I really invite you to join me. Since it's 2016, we do not need to actually, you do not need to be part of a team like join and have commitments and anything. It's on GitHub, so use GitHub magic, merge, pull, fork. Okay, now we really need the slides, please. Perfect. A round of applause. Okay, so for anonymity, the demo, the source code on GitHub actually includes commented out lines that does these two things for anonymity. You can consider not including the real source IP even in the metadata. Thus, even the server will not be able to tell who the client is. So full deniability, no logs. Fun, huh? You can alternatively consider not sending the packet from the real source at all. If you do both these things at the same time, of course, the server will not be able to reply you. But if you do any single one of those separately, server will still be able to send you the reply without knowing your IP address in the first option here, and in the second option without highlighting your IP address at all on the network level for third-party adversaries. In general security, well, there is work to be done to check the validity of the crypto, of course. We would need to think about key management. Static shared keys suck, so something has to be done about that. A penetration test is in order, some fuzzing maybe. We might think about obfuscation. Currently it's super easy to detect that it's SIPSA. You just look at the first 5 bytes, that's a SIPSA. Some other ideas. IPv6, of course. I might actually be doing this one myself, unless someone sends a pull request before I'm able to finish this. It's also currently already possible to include random seed instead of the IP map, instead of the full IP map in the metadata. Thus, we have smaller metadata and smaller payload, and smaller datagram. We can have stateful SIPSA. This will give a bit less bandwidth usage, but we will abandon some privacy as it might be possible to detect when a new connection gets created. And NAT, of course. It's a hard problem, I would say, even more so than BCP38. So any ideas, even not in written form, just come talk to me. Any ideas about having SIPSA work over NAT would be appreciated. So to conclude, please give me feedback. You can say it sucks because there's a reason. You can say it's great and we should use it in products, whatever. Please fork, implement it in real world if you think it's useful, if you think it's sane. Okay, I clicked on a link because it is a link. So okay, here's the link to my GitHub. And here's my Twitter. So, yes, so that's everything from me. Thank you very much. If there's questions and we have some time, then it's the time. Or feedback already. Yeah, can we get Mike?
Hi. You said something about protocol obfuscation because every snort or bro is going to pick up these packets running Just
Yes, I did.
any kind of sniffer. What can be done about hiding the fact that you're using it?
Well, you know, there are multiple protocols already that are being obfuscated. Tor namely has some sub-protocols. Well, as a long-standing fan of TrueCrypt, we could use that and send over the network, so and then see if it decrypts or not. But of course, the real threat here is active fingerprinting is used by Great Firewall of China allegedly. So, well, we need more smart people to fix that. Any more questions, suggestions? Anybody already installed and tried on your own? Did it work? Okay, well, you have the link, you have the time. Oh, we have a question. Yep. Is that the final question, or do you have any more questions? Okay, great.
If you do know the address you get hidden behind, if you do a hide nut, in theory it should be workable if you included the address where you're going to be hide nutted behind in the list of the IPs.
Sorry, can you repeat that again? Maybe microphone a bit further from you.
You mentioned that it doesn't work with hide nut.
Yes.
Reason probably because you include your original IP address in the list of the IP addresses,
Yeah.
but later on it gets changed to another one that you don't know prehand. But if you do know that you're going to be hide nutted, you could easily exchange your true IP to the one to be nutted, right?
Okay, I get it. Yeah. So in one version of the protocol, in theoretical version of the protocol, you can actually not include your real source IP address at all, and it will work. The problem with NAT is that your local router will translate all the addresses to the same output address, and you do not have control over that. And all your packets will come out with your real internet-facing address. Okay, so I see there are no more questions, so thank you very much for joining me, and have a great conference.